So, hi everyone. Today I'll be introducing like how GPU code generation works in IREE. And I mean, don't worry if you are not deeply familiar with GPUs. I'll start with the basics and then we'll build up from there. Like by the end of the session, like you'll have a good understanding of like how the IR looks like when you want to target GPUs. Uh, yeah, I'll not. Okay, yeah, that's how I want to get started. So the overview of the talk is pretty like neat, I guess. So uh, we'll go over like how GPU architecture works at a high level, then how we schedule a matmul kernel on GPUs, and then we'll look at like how some of the IRs, like some of the levels of IRs look like in IRI, basically explaining like how different things look like over there. Okay, so at a very high level, a GPU is made up of many compute units. Now each compute unit contains multiple processing elements like ALUs, register, shared memory. And GPUs have like many compute units. So compute units can be termed as SMs in NVIDIA, and in AMD, I guess it's compute unit. So now they've worked together to process like thousands of threads at once. In this diagram, the compute unit is connected to high bandwidth memory, and there are multiple levels of hierarchy. That's why there is a dotted signs over there, such as L2 and L1 cache. Now, which is missing in this picture for simplicity. Like I don't want to cover all those details. Now, to give a count of like number of compute units in MI300X, which is AMD's data center GPUs, it is around 304 compute units. Uh, Now, let's take a look at like what's inside a compute unit. So we have several important components, like a SIMD unit inside a compute unit, and they handle vector operations, processing many data points in parallel. Each lane of the SIMD unit can access local registers. That's why there's registers. The lanes of SIMD unit can share data with each other through the cross-lane operation, which we'll be discussing later, like detail, and how we basically target those instructions as well. And shared memory is fast on-chip memory that all threads in a thread block can access. We'll also look at some terminology because it might be confusing, like what's thread block and how do you access all those. So basically just keep in mind like all the threads in a thread block can access the shared memory, and that's how they synchronize. So a thread block is a group of threads that run on the same compute unit and cooperate using shared memory and synchronization. Uh, Now we took a look at like the high bandwidth memory, the shared memory, and the registers. Now they have some uh, properties like registers offers the lowest latency and are used for immediate computation by individual threads. Similarly, the shared memory is much faster than the global HBM and allows threads in the same block to share data efficiently. And HBM is the main GPU memory. It is large, but it has much higher latency compared to on-chip memory. So, and think of shared memory and registers as on-chip and HBM away from the chip, so off-chip. So just to summarize, registers are fastest but smallest. Shared memory is mid-sized and fast, while HBM or global memory is largest plus slowest. The efficient GPU programming relies on maximizing use of registers and shared memory to hide the high latency of the HBM. So I'll go over some of the hardware and software terminologies. Now, this basically helps to bridge the terms we use in hardware in terms of GPUs and software when working with GPUs. Till now, if there are some questions, I can take it. Otherwise, I'll just move on, I guess. Okay. So, so a compute unit or streaming multiprocessor in hardware is the physical component that runs computations. In software, this basically, as a software point of view, Like what I see it as a work group or thread block, which is a logical group of threads scheduled to that particular hardware. Now, SIMD units, which process multiple data elements in parallel, are conceptually they, they are aligned with WAPs, waves, or subgroups. Like these are different terminologies uh, that people tell. So, wave is an AMD terminology, WAP is NVIDIA's terminology, and subgroup is basically like OpenCL kind of terminology or Vulkan terminology. These are group of threads that execute the same instruction together. And at the most granular level, a lane in hardware is handling one piece of like thread corresponding to work item or thread in software, which represents like a single unit of execution what it does. So understanding this the software part and like where do they run on, like which hardware unit they execute on, like it helps to like clearly reason about like what's happening in the hardware, like in the GPU hardware. So yeah, I'll move on. So this is a simple matrix multiplication kernel that we're looking at. Now, I have deliberately taken the sizes with this because I don't want to target tensor cores and like show different instructions. I just wanted to keep it simple. Uh, so this is a matrix multiplication kernel. This has three nested loops. It reads half precision and then converts it to full precision, multiplies them, and accumulates them in float 32. So this is basically the kernel that we'll be looking into. Okay, so this is like how we will schedule this particular matrix multiplication on the GPU. Uh, so this diagram explains like how we break down the matrix multiplication task and distribute the work across the GPUs efficiently. So first we split the workload across work groups. Uh, Each work groups handles one dot product of two 816 elements. So if you see over here, I think I can use this. So we are just distributing this M and N dimension across the compute units. And we are just focusing on like each compute unit will be performing the K dimension, which is the reduction dimension. So basically each compute unit will be performing this part. Okay, so first we split the workload across work groups. Each work group handles one dot product of 200 to 816 elements. Since our output matrix is 2 cross 1280, we need 2 cross 1280 such thread blocks. Now within a work group, now focus on this. So within a work group, each thread performs a small part of work. Now, a single thread does a 4 reduction using its own registers. So in this case, I've taken the subgroup size to be 64. So the, the subgroup will be reducing 64 cross 4, which is 256 elements. So it will effectively do 256 reductions, but we'll be using the special cross-lane operation to do the intra-subgroup reduction. Now, once the subgroup does the reduction, we will store the element in the shared memory after that. So ineffectively, the shared memory will have 2816 divided by 256, which is 11 elements. Uh, okay, I'll clarify that. Just one sec. So what was the question again? Like I'm not able to see that. The chat. Yes.
So the question is, M and K are lane or subgroup or compute units. So what does M and K correspond here?
Okay. So M and K correspond to the basically the dimension of matrix multiplication. They don't correspond to the lane or subgroup or group IDs, whatever. So M N are the parallel dimension, the outermost dimension of a matrix multiplication, and K is the reduction dimension. But this is the terminology that I'm used to. I hope that is clear,
Okay,
I
I think
guess.
yeah, I think you can also put it like m cross k times k cross n,
Yeah,
and yeah, the
yeah,
accumulator is like m cross n.
yeah. So, so yeah. So subgroup is ineffectively performing 256 reductions, and we are using a cross-lane operation to do the intra-subgroup reduction. We are storing each of the element to the intermediate element to the shared memory. Now the shared memory contains 11 elements, 28160 divided by 256. We are again distributing from the shared memory to the lanes of the subgroup, and then doing an inter-subgroup reduction. And then each compute unit will actually calculate a single element, and we are just storing that back to the HBM. So, so this is like what is happening, like what our schedule is like. This is like the blueprint of like what we want to do right now. This may or may not be efficient, but this is what we want to do. Yep. So I hope this is question like this is the, I think, the meat of the different things that we're looking into. So if you have questions now, you can just clarify it. I can just clarify over here.
Uh,
Yeah, Jainam has a question. Yeah.
yeah, I
Mhm.
have a question. Could you explain like why are we doing these intra subgroups and inter subgroups reduction? How are they different? And what are the other methods that are being used to perform?
Uh, so 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 why are we using the intra subgroup reduction? So these are hardware dependent operation because so okay, let's just go over here. So in this case, like there are 64 lanes in the SMD, and you don't want to you just want to communicate between the SMD lanes. You don't want to use the shared memory. That's why you can do the intra. I mean, you can communicate uh, between the lanes, and then you can basically ineffectively reduce the element over there. And this is supported by the hardware. So there are hardware instructions to do that. That's why using we are using this intra subgroup reductions.
Okay.
What was the next question?
Like are there any other methods that are being used to calculate to perform this matrix multiplication other than intra subgroup, subgroup, and inter subgroup reductions?
Uh, you can just use the normal ALU to do that, like the vector ALU unit to do this. There are tensor cores instructions also to do this, like they're really fast. Uh, so yeah, I mean, you have a lot of things. Like
Yeah.
yeah,
So
the
this,
design space in case of GPU is like big.
yeah, so this is very much
Mhm.
dependent on what hardware you're using, what kind of operations it would support. Is it?
Exactly. Yeah.
Right.
Yeah.
Yes. Right.
So yeah, yeah. I don't want to get into the hardware details. Like there are a lot of things which is happening right now, and even this slide is like what I'm presenting over here is like it can target the MLIR architecture, which is around like 5 years back, uh, and and like in the Hopper and Blackwell architecture, like this is very different. Like they have third block clusters, and some of the compute units can communicate with each other. Yeah, so it's very different. But
Okay.
that's why I don't want to go into like hardware and things.
Right. Right.
So,
Uh,
so I hope this part is clear,
Yes.
and I'll
Yes.
move on. Okay.
Yeah.
I have
So
a question. So this is
yeah.
a portable way, right? It'll also work across AMD, Intel, NVIDIA GPUs, right? The concepts also are
Yeah,
portable.
yeah. This will be portable to AMD and NVIDIA architecture because they have like exact operations for this. But I don't know about the Intel architecture. Like I haven't seen that. So.
Okay, thank you.
Mhm. Okay, so this is the MLIR version of the simple matml kernel that we were saw in Python. Now you'll notice familiar patterns here, looping over indices, multiplying values, and accumulating them. But unlike raw loops in Python or C++, this version uses lineage.generic and affine maps to describe the iteration space and the relation between the iteration space and the data access space. So I won't go into the details of MLIR or dialects here, but I think there are really good videos and talks available online. Uh,
Prashant,
so this is
sorry to
Mhm,
interrupt. There is a
mhm,
question in the chat. So if
mhm.
matrix is large to not fit in shared memory, how is compute done?
Uh, we generally tile the matrix to fit in shared memory. Like it cannot go beyond the shared memory. So yeah.
Yeah, please continue. Thank you.
Oh, I think there was some lag. I hope it's good. Like we're able to hear.
Yeah, we can hear you. Oh,
Okay. Yeah. So this was the macro kernel. Like, basically, you can see the details in Lineage dialect and the Arith dialect, Punk dialect. So basically, to understand this layer, but it's essentially the same thing. Like it's performing the matrix multiplication. Uh, so I have shared all the repro commands. Basically, you can download the MLIR from here, like this MLIR, basically copy paste. You can install IREE base compiler and Python, create your own virtual environment, and then just install it. You have to run this IREE compile command, and basically you dump each of the IR. And in this case, I'm targeting IREE hip target GFX 942, which is again MI300X. And you can basically see the different levels of IR and what it is generating. And you can go to this website. There are uh, instructions about how do you actually see the assembly of the generated instructions and basically see whether it is optimal or not and what else can you do to generate the optimal instructions. So these are the reproducible commands. Okay, so we'll start with the uh, first part. Now, this slide shows the point where we attach a lowering config to the kernel. The configuration that you just have to look at the bold parts. The rest of the parts is like the same as like what I've shown, mostly same. There are some runtime bindings, but I'll not go over that. So this configuration tells the compiler how to schedule and distribute the computation across the GPU. So we do this by adding attributes like translation info. This is a function attribute, and the lowering config to the function. These attributes are what guide the GPU code generation process. Uh, so we'll take a look at that. Like, let's take a look at like what's translation info. So the translation info has first the pipeline, which the pipeline determines like which set of passes it will go through. Now, LLVM GPU vector distribute has some set of passes, and basically the pipeline guides those passes. The workgroup size is 70411. This means each workgroup has 704 threads in X direction. The other dimensions are one. So the Y and Z dimensions, basically you can ignore them. Like there's nothing over there. Uh, the subgroup size is 64. Uh, we are targeting the max of subgroup size because MI300X, like you can, the subgroup size basically 64 in case of MI300X. So basically on AMD and NVIDIA GPUs, this maps to warp or wavefront, the subgroup size. So this is the translation info. And now let's take a look at lowering config. Now there are three elements in the lowering config, right? These are three elements in the tuple which specifies the tile sizes for M, N, and K dimension. M, N are the parallel dimension, the outermost parallel dimension, and the k dimension is basically the reduction dimension. So the partial reduction 0, 0, 2, 8, 1, 6 is basically, this tells us the reduction is happening across the k dimension, which is 2, 8, 1, 6 wide. Now it's not a full reduction, but a partial one. But in this case, yeah, we'll go with detail about these reductions and what's happening. The subgroup basis tells this tells the subgroup counts across dimension. So you can ignore the uh, y and z dimension, but across the x dimension, it is 11. Now this basically corresponds to how many subgroups will be formed. So we took a look over there, look over here. The shared memory contains 2816 divided by 256, which is 11 elements. But these are coming from the 11 subgroups which are being found. So this is basically the subgroup basis. The thread is 0, 0, 4. These are the thread tile sizes. So we determine that single thread does 4 reduction, and hence here is like thread tile size is set to 4. The thread basis determines the number of counts, the number of threads that are being formed. It is 64 because the subgroup size is 64. So they basically they both correspond to each other, but you have the option to tune it further. Like you can set it to 32 or whatever. So this tells you the thread counts across those dimensions. The work group is set to 110. That means you are just tiling the m and n dimension by 1. Basically, you are just performing a reduction across a computer net, and you don't care about like the m and n dimension. You're just distributing it among the computer nets. But basically, you can change it. You can increase the work group tile sizes and see what works and what doesn't work, or whichever is performing. Like, are there any questions over here?
Yeah, there is a couple of questions in the chat relating to
Okay.
the previous slides. So there's a question on how do you tile them? What methods do you use? And the other question is, does the layout matter row-wise or column-wise?
Layout does matter. Like GPU's layouts is like one of the most important things, I guess. In this case, this is like simple. Like we are just distributing the m dimension, and we are just tiling across the k dimension. So yeah. So
No, the question
basically,
is
the
how do you
layout
tile
does
them,
matter.
right? What do you use? How do you? What is the strategy for tiling?
Yeah. So I'll just describe the first thing, that memory coalescing is very important thing in GPUs. So how you have placed the layouts will affect coalesce loads or not. Uh, so I think it does matter. But in this case, since we are accessing a k dimension, uh, like since we are accessing the k dimension, which are placed contiguously, so it doesn't matter right now because it will always give you a coalesced load. What was the next question? What is the tiling strategy? So currently the tiling strategy is greedy. Okay, so I'll go over the tiling strategy, how it selects these tile sizes. So on AMD hardware, we can do 128-bit loads from the global memory. So that means that each thread can perform. So in this case, what it does is, since we have F16, and output is F32, so it takes the maximum of all this, which comes down to 32-bit. So it will divide like 128-bit by 32-bit. So each thread can load 4 elements, is how it is determining. And based on that, it's going backward from there. So each thread is determining 4 elements. Your subgroup size is 64. So now you can basically do 256 reductions at once. So that's why again it is dividing the partial reduction with 256. So there will be 11 subgroups, and that's how it is determining the tile sizes. So currently it's greedy, but the thing is that good thing about the lowering config is that you can basically change the lowering config over here, and it will generate some code. You can basically run that code and see whether how it performs. So we have a tuner uh, which takes this Luring config, changes it has some sort of correctness method that determines that this is the correct Luring config, changes the Luring config and generates code, and then sees whether that code is performant or not. Yeah.
So there are two more questions.
Mhm.
So when we write kernels in CPP or Python, should we be aware of MLR dialects or to write optimized kernels, or compiler does all of them from high level language to MLR dialects?
You don't have to be aware of MLIR, I think. I mean, you just have to aware about like which instructions are you targeting uh, for the GPU. So yeah.
How do you choose the instruction set from the IREE config, or is there a way to specify it?
The instruction set, like if you want to, okay, so that can't be chosen right now. So that is predetermined. Like if you pass it through the LBN GPU vector distribute, that has set of passes that will determine like which instructions will be chosen. So yeah, like this is a compiler. Like there are some things that we can't do, but you can use like there are libraries like TK Wave, which is built on this, in which you can specify uh, which instructions you want to target, and it will generate code based on that. So
Okay, so the other question is, does IREE have any optimization process like task fusion that can detect and fuse independent kernels? For example, two independent matrix multiplications into a single kernel launch. While compiler, uh, while a compiler could generate such fused code manually, it would be great if IREE provided automated support for it for this kind of optimization. Is there a pass in IREE that handles this?
yeah, so there are passes in IRE. Like I wanted to show just the matrix multiplication, but you can basically do uh, matrix multiplication followed by element-wise operation. I don't know, like matrix multiplication followed by matrix multiplication and fusing them might be a good operation, but we have something called as attention, and it can also be fused like so. So yeah, there are tile and fuse passes in IRE, and basically it uses that. And it happens like much before, I guess, oh no, it happens like after that. So yeah. Are there more questions?
I think that's it in the chat. Yeah, please continue.
Okay. So yeah, so this is just telling like, so essentially this particular configuration is giving a compiler blueprint that how to split the work, how to map it onto threads and subgroups, and basically how to reduce the data efficiently. Like, so, uh, yeah, so now we'll start taking a look at like how do we distribute to work groups now. So you've seen like each compute unit has since we only care about the k dimension and we don't care about the mn dimension, so it's just distributing uh, the outermost dimension to compute units greedily, and each compute unit is basically calculating a single element of C0. So, so this is how the distribute to workgroups is like should eventually see like uh, each compute unit should only access the entire k dimension of A and B matrices, and it will perform the reduction and it will store into the C matrix. Uh, so so we'll take a look at this. So it starts with the tile and distribute to workgroups using for all pass. And if you have, so you're talking about whether we can fuse the kernel or not. This pass also does the fusion as well. So if you have uh, let's say, uh, uh, a matrix multiplication followed by a matrix multiplication, and they both share the same Taylor dimensions, it can basically fuse them. So So yeah. So we'll look at the first thing. So this is SCF dot for all. You have to like there's a very good documentation for SCF dot for all over there. So the slide shows how IREE uses the SCF dot for all construct to tile the workload and distribute it across GPU workgroups. Uh, this is a parallel for loop from MLIR's structured control flow dialect. It can be read as run the body in parallel across all combination of arg0 and arg1, which in this case ranges over a 2 cross 1280 grid. Each iteration of the loop is responsible for computing one small tile. Uh, I mean, one element of the C matrix, basically the output matrix. So we look at this. So the extract slice is basically, this part is extracting the A matrix. So it's going over arg0, which is ranges over 0 and 1. So it basically, as the name implies, like it is extracting a slice from a bigger chunk. The extract slice 0 is basically the B matrix, and extract slice 1 is the output matrix, which is 1 cross 1 in this case. Like if you do a matrix multiplication of this, we'll find a output as 1 cross 1 matrix. Now, you'll see now the linear generic is accepting these slices, right? So now it is accepting this extract slice 0 and extract slice 1, which are like, that just contains the K dimension, right? And this is outputting a 1 cross 1. So this is what is happening inside. This part is what is happening inside the compute unit. And it is basically performing the reduction across the K dimension. And then this block, it's basically they are synchronizing over here. They are basically storing it to the global memory. So whatever is stored over here, whatever is calculated over here, this %8 is basically stored in the output, which is our global memory. So this is how the time distributed workgroups using for all works. If you have any questions over here.
So how does IREE determine synchronization?
What do you mean by
Like,
synchronization? As in, like, could you explain
so
more? Like,
once you compute the reduction, you need to store back to shared memory, right? So which means you need to
yeah.
wait.
So that will be determined like afterwards. Like this is agnostic. Like currently, this is agnostic to the hardware. So yeah.
Okay,
Uh,
okay, thank you.
these are generic passes. These are generic passes, as in these are like, if you're targeting compute units, you can think of like this as targeting cores on the CPUs. Like there are multiple cores on CPUs, and you just want to distribute data among them. So this can be used on CPUs. This can be used on GPUs. Yeah. So currently, we'll look into synchronization later, like how it is creating barriers. So yeah. Mhm.
Okay, got it. Yeah, thank you.
Next. So there is, again, it goes through the GPU apply tiling level pass. Now over here, you'll see that the partial reduction size is 2816 and the K dimension size is again 2816. So in this case, like it won't do any tiling over here. So, and this is a reduction tiling, so it won't generate a CF.4 over here. But basically, like I wanted like to uh, like you to play with this. So basically increase the K dimension and see what tile sizes it will select and basically tile it. So, um, so yeah, like basically experimenting with something. Uh, I'll go over to the next pass. Now, this is one of the important passes. Like this steps performs a data flow based layout propagation, where a specific tensor layout is attached to the anchor operation, and that layout information is propagated back to its input. In this case, the anchor operation is basically the output of the linear search generic uh, that performs the element-wise multiply and add. The layout determines how the data is distributed among threads and subgroups, and the computation should be aware of that. Now, this particular layout is determined based on the tile sizes that we already saw. Uh, so, and it is attached to the anchor operation, which is the output of the main lineage.generic. And basically, it is propagated backward. We do a backward data flow analysis and then basically attach these operation to the layout information to the inputs of the lineage.generic, right? So I didn't want to go more into details into this because this is a heavily involved pass. So there is a like Kunwar, one of my one of the members of team actually presented a like good introduction about this, like how this works and all. So there is a YouTube channel that I have, like YouTube link that I've attached over there, like talks about more in detail. So maybe you can see that. If you have some questions, I can answer over here.
So there's a question. So these
Mhm.
passes are applied before ID specific dialects, flow, stream, HAL.
Uh, no, these are applied in conjunction with the flow, stream, and HAL dialect. Uh, yeah, I think the HAL comes after that. So flow and stream are there. The HAL comes after that. So yeah. Okay, then I'll move to the next pass, like which is I think the last pass, I guess. So after this pass, there is a LLVM GPU vector distribute pass. Now, at this point, we are no longer working with high-level tensor information or abstract layout info. We are now telling the GPU what exactly each thread should do. So, so this is like the entire blue, the thing that I showed earlier. Like this pass is basically this thing. So I'll go over details over that. So, so the pass distributes the computation across individual threads in our group. It then extracts specific slices of the input tensor that each thread needs to perform the computation. Uh, if the thread tile sizes was set to 4, now you'll see that we are reading 4 elements because the thread tile sizes were set to 4, and we are reading from the global memory. And again, we are so these are the LHS and RHS, which are set, which are of size 4. We do a XTF, which is converting from float 16 to float 32, increasing the precision. We are doing a multiplication of it, then addition, and then we are doing like the reduction. Now, this is happening at the thread level, like what each thread is doing. After each thread does its calculation, we are doing a subgroup reduce operation over here, which is basically reducing all those 256 elements, like the cluster size was set to 64, to a single FP32. Uh, we are allocating a memory. Now, this is GPU address workspace workgroup, which is a shared memory. We are doing a barrier, like we are creating a barrier over here, like someone talked about that. Uh, so we are creating a barrier and we are writing everything to the shared memory at this point. Then we are basically distributing from shared memory to the lanes again, like the shared memory size is 11. We are basically reading everything from that. Then we are again doing a GPU subgroup reduce operation, which is of size 16. We cannot do size 11 because it always has to be a power of 2. But since we are like, we know like we are distributing zeros to other dimension, other lanes, so it doesn't matter. Like it can, like you can increase the size, but it will do the right computation. And then we are directly writing, like each thread is basically, each computer unit is basically writing single element, which is a vector of FP32, like can we think of like a single element to the global memory. So, so yeah. So basically we had 704 threads, and each thread was performing like 4 elements, like a reduction of 4 elements. So ineffectively, you are performing 704 cross 4, which is 2816 element. Uh, I'll go over the GPU subgroup reduce operation, which is very hardware dependent. And so So what is a subgroup reduction operation? Like this slide shows a tree-like reduction pattern happening within a GPU subgroup of size 8. So each vertical arrow represents a value, like this arrow, the curved arrow, represent a value being passed from one thread lane to another and basically combined. And we are doing it in a tree reduction fashion. So after doing it for 3 levels, we have a single element over here. So, and this is very architecture dependent. Like AMD CDNA 3 architecture, this communication is efficiently handled by the cross-lane transfer operation. There are 3 operations, like TPP, permute, and sigil operations. Uh, yeah, so this instruction let lanes read from neighbors without going through the LDS or shared memory. They might use the unit, but they generally don't use the memory, which makes the reduction like much faster and more hardware efficient. So there's some information that I've added over here. So basically, people can take a look at it. Yeah. Uh, yeah, so that was it, I guess. If you have more questions, like I can take. Hello?
Thank you, Prashant. So are there any
Yeah.
questions?
Could you explain how the subgroups, the last option that we're talking about, the
This
last,
one?
yeah, the subgroup reduction, how is
Uh-huh.
it hardware dependent? Like what changes with what the change happens in this function when hardware changes?
Yeah. So generally a GPU dot subgroup reduce is not a hardware dependent operation, but its lowering can depend on which hardware you're targeting. So it will go through different dialects. So if it is a AMD, then it will go through ROCDL dialect. If it is NVIDIA's, then it will go through NVVM or NVBTX, whatever, and it will select a particular operation required for the cross lane swizzling. So, so that makes it hardware dependent. Yeah. But currently you can see like this is like a GPU dialect operation. It is hardware agnostic.
Right, makes sense. Yeah.
Mm. Yes, it is very compatible with Torch compile. Yeah, there is. I can share links. I mean, we do that. Like,
Yeah, you can share the link. If there's anything else that you need in the recording, then you can tell us. We'll put it in that also.
yeah, sure. Yeah.
So there's a question on, are there any resources to go through to get started with compute and GPU?
Uh, I think there are a lot of YouTube videos. You can basically go through that. I think there is one video that I really liked was from Safari group. They talk about like architecture in detail, and that might be useful. How is IRI different from the GPU dialect? Uh, IRI is different because GPU dialect is just a dialect, right? You have to target that somehow. You have to use those dialect instructions or operations present in the dialect. IRI does that. And IRI is just not a compiler. It's basically, it has a runtime function and basically hooks onto that. So yeah, it uses GPU dialect, but yeah, IRI is more than GPU dialect. I don't know. There was not many questions. I anticipated like there will be a lot of questions, but anyways, like
I think people took questions in the middle also, right, during the talk. So that's why.
Okay. Yeah, there are resources for beginners to work on building compilers. Maybe I'll share them. There is a very good course on that. Um,
But is there any course on building compilers for ML models?
yeah, there is a course MLC.ai, I guess.
All right, from
So
CME, right?
yeah, yeah. I mean, Tianki was not in CME back then, but I think he went over there. But yeah, it's a good course. Like, it is a different compiler. It is TVM, but the principles apply over here. So yeah. Can you explain where we do inject flow and stream dialects in these passes? So basically, you can see the IR dump. It is the flow actually determines the runtime bindings. So basically, if you see the okay, so if you see the inputs over here, the HAL.interface bindings and all sort of things. I mean, I have not zoomed it. So this determines like how we are handling the inputs, and and basically these are applied like very early. So basically, if you go over here and see the IR dump, you'll find everything like which passes are actually doing injecting flow and streams and everything. What are your thoughts on the different approaches in GPU compiler space, TinyGrad, TVM, MLIR? Uh, okay, so I want to touch on this topic because this is like very important. So, so in fact, I think there is Triton, there is uh, there is Palace, which is again a DSL from Jack's team. There is yeah. So there are many approaches now. How they target is important. I think Triton works at the block level. They don't expose shared memory and everything to you, but you can determine the block sizes, which are ineffectively the workgroup sizes. In We have something called as TK wave, in which you can actually compute at the shared memory level. You can actually specify instructions at the shared memory level. Uh, yeah, so I think there are different approaches, and 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 basically how much time do you want to write a kernel depends on that. Like in IREE, we give you, it's like a GCC of ML compiler. It will work for many of the models, but it won't be performant. But at the same time, if you want to, it will hide most of the things from you. Uh, in case of Triton, like it's one DSL, like you have to basically understand like how it performs and basically target that. It gives you some control. Uh, yeah, that's how I think about it.
There's one more question that you missed. So does MLIR's GPU abstraction handle AMD's LDS local data share the same way it maps to CUDA shared memory?
Yeah. So yeah, I mean there is no difference. Like yeah. So basically, we attach an attribute called workgroup, and it will basically lower to, so over here, GPU address workgroup, and basically it is hardware agnostic. Like it will target LDS and AMD GPU, shared memory in NVIDIA's GPU, and so on. Yeah.
Got it. Thank you. So I think I'll share my thoughts on Triton. Triton is an interesting DSL that works on tile-based programming model. So the idea is you program with tiles instead of thread level details.
Yeah.
So Yeah, I think different frameworks have their own sort of programming model to which you can target your compiler. So Triton can be targeted from different DSLs as well, and but you can also program in Triton. But I think Triton is now being widely used DSL for AI applications. Yeah, a lot of companies are jumping on.
Yeah.
And-
In fact, I think NVIDIA also has something like they are also moving to Python bindings in Cutlass and Qtile, and then they give you. I think the problem over here is that hardware is changing very rapidly, and they have like very different instruction sets when you move from one. Like if you see Ampere was like Ampere between the instruction set between Ampere, Hopper, and Blackwell, you'll find that jump is like different, like at different level, like there are different instructions at all. So, and now there are not even three levels of programming, like there are thread block clusters in Hopper, right? And when you move to Blackwell architectures, even the thread block can communicate. There is two pair CTA. So the hardware is changing rapidly, and software is not able to catch up with that. That's why they are providing DSLs to uh, I mean, that's why they're providing DSS so the user can understand the hardware and then they can target those.
Yeah, totally. Yeah, I agree with you on that. Hardware is changing rapidly, and the software is trying to catch up. So, how does multi-node compute, example, distributed training for ML models done? What are the passes and ops for them?
In this case, I currently we don't have like multi-node distributed thing in IREE. Like it's currently it's limited to inference. So yeah, so we don't have like anything passive and ops for them. But in MLIR, I think there is a dialect that actually targets distributed computing, like that. I don't remember the name of the. I think the mesh dialect, I guess. So
I think there was one MPI dialect that the University of Cambridge team, Tobias Gross's team added.
oh, I see.
But I think I'm not aware of the mesh dialect. But I think other frameworks like, for example, PyTorch or JAX, they would have,
The Jax app, yeah. Mhm.
yeah, for distributed training um, or deployment.
Yeah, I think Jax has it. So I'm not aware of that, to be honest. So yeah, but I know that Jax has. Does IRI
So does
support
IREE,
OpenCL backend? Where does the actual CodeGen happen? Like one-to-one translation of MLIR to say OpenCL or Vulkan? Uh, I think there is something called as SPIRV, which is again an intermediate representation for target Vulkan, I guess. So in IRI, you can basically like you can specify the targets. Uh, so IRI HAL target device is Vulkan, and then you can specify the target, and basically it will generate a Vulkan code for you, and actual translation happens in MLIR, I guess, because there is SPIRV dialect in MLIR, which does the translation for you. So I'm not aware of that, the OpenCL support. Yeah.
so Krishna, any reason why you need OpenCL support? Um,
I think OpenCL is more portable, like you can target many GPUs. That's why I guess.
I think the same goes for MLIR, right? It's also portable in some sense.
Uh, yeah.
Okay.
Can you tell me how IRI will help application developer? Uh, which application do you want? Like if it is related to running ML models, then it might help. Other than that, like I don't know. Like other than that, no,
Can you,
I guess. Yeah.
can you also explain how it'll help ML deployment?
Uh, it can basically compile those ML models, right? And give you like good inference speed. Uh, so we had a submission for SDXL and it gave a really good speed on MI300X. Uh, that way it can help. Other than that, like it won't. So it's just a compiler
Okay.
for ML models.
Okay. Can you also explain what is the entry point to IRE?
Uh, what's the entry point? So there are many entry points to IRE. It can be a FX, it can be a torch MLIR, like it can be a torch IR, it can be denials IR. Yeah, those two are the entry points to IRE. It can be, yeah, those two are the entry point. I think there is stable HLO as well. Uh, those are the entry points to IRE. Do we have training support in IRE? No, we don't have. Right now, we don't have. Uh, okay, so if you, so I'll stop over there because training support in IRE we have if you provide that particular IR. So if you provide the lineage IR that has like different instructions and that uh, is basically you are updating the weights and all sort of things. I think it can lower it, but yeah, we are not actively looking into that. So, mhm. So IRI takes ML models written in CPP Python involving CUDA, HIP, OpenCL code. No, that's not it. So IRI takes ML models that is written in PyTorch, or basically it generates it basically captures the PyTorch program, generates an FX graph, uh, and basically it captures that FX graph, converts it into MLIR, and then uh, does the compiler optimization and optimize it. Yeah. So if I read it correctly, so IRI takes ML models written in CPP Python involving. So actually, you are right. The thing is that PyTorch uh, PyTorch does this. Like so, PyTorch is a basically a DSL for machine learning models, and it has a Python front end, and the backend is basically CUDA, HIP, or C++. But the thing is that we don't go to the backend. We just capture the what the PyTorch graph gives, and by tracing it, and then we lower it to uh, the dialect, and basically we capture the graph and then lower it. Custom implementation of gradient operators in denials would help training. Yeah, it can. It can, yeah. Uh, yeah. Now depends on like what you're targeting. So does IRI code converts to LLVM? Yes, for the LLVM CPU and the and even the AMD GPU backend, they convert to LLVM IR. So yeah, does IRI codes convert to LLVM? If you're targeting SPIRV, I guess that goes through the Spivvy backend. I'm not sure about that. So yeah, it does convert to LVM. It uses LVM. Yeah, backend.
I think there are more IRE questions that we should do a deep dive into IRE, like a tutorial. I think it's a point.
Yeah, yeah. I think basically, yeah. How does IRE hooks like? Yeah, you're right. Actually, yeah. The host code generated will be LVM. Yeah, you're right.
Yeah, I think that's taken care by the GP direct, right? It's not IRE, right?
Uh, the host
Yeah, the host code.
code. No, the host code runs on the host, so it's CPU. So it will be LVM, and then the device code will be something else.
Okay, I mean, does IRE do any specific optimizations for the host side?
Does IRE do any of the optimizations on the host side? No, I guess it does. Like it creates like so if you have a big ML model and then you have like dependencies, it can basically create good dependencies and basically stream those kernels in a fashion. So you don't. So there is something called CUDA graph. It can do a graph like I mean, it will create a graph for you and schedule it efficiently. So yeah, and
Okay,
I think that part is taken care by the stream dialect.
okay.
Yeah, it will follow LVM passes for the host code optimization mostly. You're right.
So how I compare to TVM CUDA slash TP based compilers?
How we compare to TVM, CUDA, TPU based compilers? Uh, I have less idea about the TVM, like what they're doing. CUDA, you have to write your own code, right? So, and that will be performant. Like if you write your own code, if you understand the architecture well and you're using intrinsics, you're using all sort of different hardware things, then it will be more performant, but you have to write the code. Uh, TPU based compilers, the TPU based compilers, I think JAX is the one. JAX is the front end for that, and uh, uh, I have no idea about like what's happening over there as well.
Yeah, TPs are closed source. I think it's only targeted by OpenXLA, I guess.
Yeah, there is PyTorch XLA, but I'm
Okay.
I'm not sure like what to do. Yeah, so basically you can write the PyTorch code and generate TPU based something.
So can you show hands-on how to generate a simple ML code to IRE? I think we'll do a separate tutorial probably in the future. Yeah, it's
Yeah,
yeah, I think it's more complex and involved. So yeah, we'll probably do that at some point in the future.